This podcast is recorded at the University of Sydney's Camperdown campus, on the land of the Gadigal people of the Eora Nation. They've been discovering and sharing knowledge here for tens of thousands of years. I pay my respects to elders past and present, and extend that respect to all Aboriginal and Torres Strait Islander people.
My name is Sophie. So I've been living with type 1 diabetes for about nearly 20 years. So I got diagnosed when I was about 14, 15. It was definitely a shock. In those first years after my diagnosis, it was a lot of secrecy and hiding of my condition. Everything was done in the toilet or in secrecy. Measuring my glucose, injecting myself before a meal would all be done in the toilet where nobody really knew what I was doing. As a teenager, you want to fit in. That's the main thing all teenagers want to do. And the moment you get the diagnosis, you know that you're different. You'll know that your lifestyle will be different to others. And you have to be more careful. I think that was why I hid it, because I felt uncomfortable being different.
For the millions of people living with type 1 diabetes, insulin is literally life-saving. Since its discovery over a century ago, it's transformed type 1 diabetes from a death sentence into something that can be managed with daily injections or insulin pumps worn 24 hours a day. But saying it can be managed undersells just how involved life with diabetes can really be. So what if insulin could think for itself? And what if it could be taken just once daily with no needles and no need to think about the dose? Professor Victoria Cogger is working on a solution long thought impossible. Smart insulin, delivered orally in the form of a single daily pill. I'm Mark Scott, and this is The Solutionists. Professor Victoria Cogger has been the director of the Anzac Research Institute at Concord Hospital, but she's the newly appointed inaugural executive director of the Sydney Biomedical Accelerator and the co-founder of EndoAxiom, a company developing oral insulin using nanotechnology. Victoria, welcome. Let's clarify exactly what we're talking about here. What is diabetes and what's the difference between type 1 and type 2?
Hi Mark, lovely to be here today. Type 1 diabetes is when our pancreas is not able to secrete any insulin any longer. It is an autoimmune condition that usually affects children between the ages of about 5 and 15 is when most children are diagnosed. Type 2 diabetes, on the other hand, is when our body becomes insensitive to the insulin that we're producing. It's not that our pancreas stops producing it entirely at the beginning, it's just that our body can no longer sense it in the way that it needs to. And it causes similar impacts as type 1 diabetes, but it is actually a very different disease to type 1 diabetes.
So the vast majority of people living with diabetes are living with type 2 diabetes. So what are the common misconceptions about type 1 diabetes? It's relatively rare, is that right?
It's a much rarer disease. It usually is a childhood onset disease, and it's not something that can be modified by lifestyle factors in the same way that in type 2 diabetes you can have impact on that disease. Type 1 diabetes is an autoimmune disease. Your pancreas literally eats itself, and the cells that produce the insulin are no longer present in your body. Your body simply cannot produce insulin any longer. It's not that you need to potentially modify your diet or potentially do a little bit more exercise or change something else in your lifestyle. It is that your body simply does not have the capacity any longer to produce insulin, and this causes dangerously high blood sugar levels, which can create a condition known as diabetic ketoacidosis, which is very life-threatening.
So you're trying to change the way that people manage their type 1 diabetes. How are people managing it now? What's the common day-to-day life experience of someone with type 1?
So type 1 diabetes can only be managed by daily injections or pump infusion of insulin. So this involves the delivery of insulin into the body either via a needle into the subcutaneous fat, usually of the belly or the leg, and they deliver insulin that way 4, 5, 6 times a day so that their body can keep up with their requirements for the insulin so that the sugar can get to where it needs to get in the body.
So this means, have I got this right, that you'll have young people, you'll have children who'll need 4, 5, 6 injections a day of insulin to stay on top?
That's right. So 4, 5, 6, or they're on a pump that they're connected to 24 hours a day.
And what does the pump do?
So the pump acts as an artificial pancreas, and through monitoring your blood sugar levels, it then titrates the level of insulin that needs to be released into your body to try and keep your levels of blood glucose or blood sugar between a relatively normal or safe level. And so basically somebody who lives with type 1 diabetes needs to be on top of this all day, every day.
I got the insulin pump. That has been a big change to my condition. Before I was injecting myself at least 4 times a day or more. And because of the new technology that has come through, you don't have to prick yourself every day as well. Obviously, you have all these machines locked onto your body, like they're stuck to your body. But there's a lot of technology that has helped to kind of minimize the blood pricks and the injections. And so obviously that has really helped because I don't really have to go to a toilet and open a needle. And, everybody don't like seeing a needle in public. But having a pump, you just take out the machine and adjust the dose for your meal. And so it has become more easier to manage in the public, definitely with the development of technology.
My name's Michelle, and I have lived with type 1 diabetes now for 31 years. I was diagnosed on the 14th of November, 1994, which ironically was actually World Diabetes Day. I was a preteen, and then I went through it as a teenager. And, being a teenager is hard enough without also having a condition where you have to give yourself medication, you have to give it attention, and you constantly have to plan what you are doing. It was very little spontaneity. And so that was always quite tricky. I guess one of the things that people misunderstand about diabetes management is often that it's just about food and it's just about your medication. And there's actually a lot of other factors that affect our glucose levels through the day. So, if I'm feeling a bit stressed one day, or if I'm feeling nervous about something, and my glucose levels can rise because of that. If I've done some exercise, then my glucose levels can go high from that exercise, and sometimes they go low from exercise, depending on what type of exercise I do. And if I want to drive the car, I have to see what my glucose level is to make sure that I'm at a safe level that I can drive my car. You're constantly planning your next move, and to leave the house, I have to make sure I have something with me in case my glucose levels go too low. I have to make sure that I have spare insulin pump consumables. So there's lots of parts of having type 1 diabetes, which isn't just what we eat.
So tell us about the work you're doing now. You're still working on insulin, but thinking through how it can be delivered differently.
So one of the things, and there are no two ways about it, injectable insulin is life-saving. And the people that discovered it and were able to separate it out of the originally pig pancreases just over 100 years ago, really, they won the Nobel Prize. They deserve every bit of that Nobel Prize. But the thing is that when we take insulin, we have to inject it. And the way we inject insulin does not mimic the way in which insulin is normally secreted by the body. And instead of going directly into our bloodstream, it goes into our subcutaneous fat, and then it travels around the body before it gets to its target tissues. And that is really not a very effective way of delivering insulin and creates lots of side effects known as iatrogenic impact. And these side effects actually can be really counterproductive to managing body weight, managing insulin sensitivity, managing infections, all of those sorts of things. And so creating a different method of delivery is something that became very important to our team.
So what have you begun to focus on?
So we really started to look at how we could orally deliver insulin. And we really started to try to understand how we could take something that is only able to be ingested or taken into the body via injection. We wanted to try and see if we could make it orally bioavailable. So it's one thing to get something into your body, it's another thing to make it available to your body. And that is what we have focused on.
And would oral insulin be that much more efficient?
Absolutely. So oral insulin, when we take something via our mouth, it goes straight into our bloodstream from our gut and directly to our liver. When our pancreas secretes insulin in people that are not living with diabetes, it goes straight into our bloodstream from our pancreas, straight to our liver. So in some ways they mimic each other. When we take it subcutaneously, it goes everywhere else.
On the circuit.
And then it comes to our liver.
And again, the dangers of it going on that indirect circuit through to our liver has real physical consequences.
Absolutely. So one of the big problems with insulin therapy is people that start it immediately put on weight because they're fat and they're just their normal, adipose tissue, and their muscles start to be exposed to levels of insulin that someone that's not living with type 1 diabetes are not exposed to. And those levels cause excess fat deposition because insulin causes fat uptake into your fat deposits and also can cause fat deposits into your muscle, which is really not something that is great to live with.
People have been injecting insulin for 100 years. What stood in the way of us developing an oral solution?
Absolutely. So lots of people have tried and we're very aware that many people have tried before us. And basically our body is really clever and has evolved all sorts of mechanisms to stop proteins, of which insulin is one, from getting into our body intact. And that's because that's one of the ways in which we prevent infection and we prevent toxicity from, things that we pick up off the floor and all those sorts of things. Our body breaks it down in our stomach with high acids and enzymes and all those sorts of things, which break down proteins into their core components. The reason insulin can't get in is because of all of those factors. And so what we have needed to do is invent a way to make sure we can protect the insulin from our body's innate mechanisms to protect it from us ingesting whole proteins.
So the stomach would normally attack the insulin before the benefits could be accrued to.
Absolutely. You would not get a whole molecule of insulin into your bloodstream. You just get bits of it. And so what we've done is we've created a way to get the whole molecule in and make sure that it can still work when it gets into your bloodstream.
So how are you going about that?
It's been a really interesting process because it's pushed us into areas that we are not, we're not innate nanotechnologists. And
what's a nanotechnologist?
Sure. So nanotechnology is really an area of science or an area of physics and chemistry where we're looking at molecules and designing molecules that are sub 100 nanometers in size. So to give you some context, 100 nanometers is about a third of the width of a human hair. So we're talking about very, very, very tiny molecules. And the reason they are so interesting is because they allow us to circumvent some of the properties that our body has to protect itself.
Is that due to the fact that it is so small?
Partly it's so small, but it's also because of some of the innate properties of the particular nanotechnologies you might like to use. We use a quantum nanotechnology, which means our dots can behave either as a wave or as a particle, and this is how we're able to get through into the body.
Now, that sounds complicated.
It is.
But explain it to us a bit more. So the molecule that carries the insulin, tiny, delivered into the stomach, and then using these quantum capabilities allows it to bypass the protective mechanisms.
That's right. So that and a protective coating, which we can come to, but the nanoparticle can behave like a wave or a particle. We attach the insulin to it and it still stays. So our dots are only about 7 nanometres in size. And then when we add the insulin to it and encapsulate it, we keep them below the 100 nanometres size. And so they continue to be able to act in that way that allows them to basically slip through the cells and into our bloodstream.
So that's the sweet spot is the 100. And
That's
if you
right.
keep it smaller than that, it's more likely to be able to make its way through.
That's exactly right.
How on earth do you load up a molecule onto something so small?
Yeah, it's a good question and involves very clever chemists. But really we have linker molecules and we also use electrostatic or negative positive charge. It really comes down to things as simple as that. Positive, negative, just like a battery, we join them together and they match up and they allow us to attach the insulin to the molecule and then we can keep them together.
This feels a long way away from, your core medical experience. First up.
Absolutely. And the work really has only been possible because of our collaborations with very clever people at the Nano Centre here. Zdenka Kunchik, for example, my co-inventors, David Lakuta, who is a clinician and has significant experience in treating diabetes, and also Dr. Nick Hunt, who is the other co-inventor of the molecule. We have really had to push into areas that we knew what we wanted to do. We needed help to work out how exactly to do it. And we've been very fortunate to collaborate with people that have been really willing to go on that journey with us.
It's a great example of multidisciplinary teams taking on the great global challenges. They talk about your pill as being a smart insulin pill. So it's not just tiny. In what ways would it be smart?
So it's clever, and this really was Nick's leap of faith for us. It's clever because we're able to coat it in a way that it is not the coating which partly protects it from the enzymes that I spoke about before in the stomach and gastrointestinal tract. It coats it in a way that means that the insulin cannot be released unless the enzymes to break down the coating are able to operate, and they can only operate in high glucose environments. So when the body has low blood glucose or low body sugar, the insulin is hidden and it's not bioavailable. And so in doing that, we make it smart because the insulin can only impact the body in the same way that the pancreas works. The insulin is only active when there's sugar in the blood. In low sugar environments, the insulin just stays tightly wrapped up in its little package.
So if I go back to the current treatment, which is all about the pump and the measuring and then delivering the necessary dose, the medication itself only works if the condition is set that the body really needs it.
That's exactly right. So the enzymes can only work if the body needs it.
It sounds incredibly exciting. Tell us about the journey from taking smart ideas in the lab on a process of development whereby you've got the drug and then trials of the drug and possibly changing the world as a consequence of this.
Mark, it's been a phenomenal process. It has been a learning curve like nothing else I've known in my life, and it has been a wonderful ride. We, again, needed to lean into areas of complete discomfort and interact in ways with companies, in ways with investors. We really had to work across the basic discovery side, pushing into clinical experience and all of those sorts of things. So through collaboration, we were able to understand what the problems are with insulin delivery. So all of that sort of thing was incredibly important. And then basically we needed to go and learn how to pitch our ideas to people that were potentially going to help us get them out of the lab and into the clinic. We've had to learn about manufacturing. We've had to learn about regulatory affairs. We've had to learn about all of those sorts of things. But luckily we've been supported to do that here. And that has been something that's been really important. The other thing that really helped us was partnering with the business school was incredibly important. And also we were very fortunate to receive a philanthropic bequest that really helped supercharge this project.
One of the things you've demonstrated is the power of business partnerships in this work. Tell us a bit about Proto-Axiom and Endo-Axiom.
So Proto is a biotech accelerator here in Sydney. It's a fairly new company, and Anthony Liveris came into the market to disrupt and try and help to accelerate biotechnological advances that are coming out of universities. And so he really came in with some venture capital and has raised funds and done series raises and all of those sorts of things so that he can start to help to license intellectual property out of universities and medical research institutes into the corporate space so that they can start to get the support and traction and business development that they need. Obviously, you need to do clinical trials. They're very expensive. You need to do all of the regulatory things that I spoke about. All of that stuff needs know-how and needs support, but all of that costs money. And so really the partnering with Proto so that we could spin out with the University of Sydney and the Sydney Local Health District to form Endoaxiome is what is pushing forward our oral insulin into the clinical trials that are currently getting ready to get underway.
And how long will that take, that clinical trials process?
So the clinical trial will take 6 months, the first clinical trial, and then after that we'll move into phase 2, and that will take another 2 to 3 years. And then the phase 3, that's when it starts to go worldwide and starts to be sort of incorporated into clinical practice, but in an experimental way. So we're still a few years off this hitting, the shelves as such, but we're well and truly on the path. And for me, that is a moment of huge fulfilment.
I think the biggest thing would be if I could just sit down and eat some food and not have to think about it 15 minutes before and not have to count my carbohydrate foods in my meal and worry that I might have calculated it wrong. It's one of those things that makes me not always want to try different foods because I don't want to have to deal with it afterwards. So I think for me, having something which means that I can just eat something without having to count the carbohydrates in it and without having to worry about the repercussions of it afterwards.
Now, you're not just a scientist in this space, you're a caregiver to someone living with type 1 diabetes. But that came later. You started the work first. Tell us this story.
Yeah, so my son was 10 and we had already finished the oral insulin formulation, the one that is going into people, and we just finished it. And he was not very well, and it was through COVID. So, it was, as we all know, the medical system was so under strain. And he got terribly, terribly unwell one Christmas. And I didn't know what was wrong with him, and I thought he had a virus. He was rushed to hospital, and by the time I had no idea what was wrong with him, even though I work in this field and had so much experience. So you
didn't think this is diabetes?
Not at the beginning. And when I look back, I'm aghast because I think, how on earth did I miss that? But I rushed him to hospital, and when I got to emergency, I said to them, my son either has type 1 diabetes or he has a brain tumour. And they said, well, let's check the type 1 diagnosis first. And his blood sugar levels were 30-something, which normally they should be 5. And he was very, very acutely unwell. And the team that helped him, sort of helped us support him in those first few days were phenomenal.
I can imagine this just creating this massive, complex, almost psychic reaction from you. I mean, devastated as a mother that your child is so sick, relieved at a diagnosis, but of all the diagnoses for him to have, it being the area that you've committed your professional life to. How did you come to terms with that?
It was a big head wrestle for quite a while. I was very worried for a long time. I'd brought something home from the lab and done something to him. And that was something, and it took his endocrinologist and everything to say, it
doesn't happen
Vic,
like that.
This didn't happen like that, calm down, it's got nothing to do with you. But I think what it did for me and the project, and I think the way I then worked with our team, was it made it something that I was able to say, this is going to make a tangible. It took it from something that was abstract to something that you really started to understand what it is like for someone that is having to live with multiple daily injections or a pump, and you see how it changes fundamentally the activities of daily living. You have to think, what are we eating? What are we doing today? What do we need packed in the car? Particularly when, he was little, and, he's not so little now, he's giant. But, he loves football. He loves his sport and all that, and it really does change the way you think about it. And who's going to be with him today when he's playing sport? Who's going to make sure he's got his juice in his bag, his things in his bag? What's at school for him to make sure that he is going to be okay if he has an event at school?
Yeah. So it brought you kind of deep empathy and insight into patients and I suppose into carers, into families. Did it change any of your research as a consequence of that?
Absolutely. It changed it to something that I knew needed to be addressed, and hopefully we can create a technology that not just delivers insulin but can solve this problem for other proteins as well. So all protein-based drugs need to be injected. And this sort of technology, it's like we've designed a new suitcase for the protein. And if we can impact other diseases in this way, I can only hope that we can change the lives of other people as well.
So if you crack this delivery mechanism, what are some of the other diseases that might be helped through this?
So there are lots of diseases that need injections. Things like children that have stunted growth or limited growth require human growth hormone injections. There are other diseases that the GLP-1s, the Ozempics and all, they're protein-based drugs.
Right. So you can take a tablet for that.
Absolutely, rather than an injection. It also makes it cheaper because you don't have a lot of the issues that are related with injectable drugs. We've spoken about the issues to the person, but also protein-based drugs need to be refrigerated. They need to be cold stored, transported. They have limited shelf lives. This has major socioeconomic impacts.
So no pressure, Victoria, but the biggest building we've ever built here in the 176 years of the University of Sydney is the new Sydney Biomedical Accelerator, and you've just been appointed the inaugural director of that new complex for us. Tell us about the opportunities that you think the Biomedical Accelerator could bring to the treatment of patients and the development of new drugs and diagnostic tools.
So for me, and I think the University of Sydney and the Sydney Local Health District and the people of New South Wales, the Sydney Biomedical Accelerator is going to transform the way in which we, as a university and a local health district, can both treat the patients that we have and design new treatments for the patients in the years to come. We are taking a relationship that's been in place for, I think it's 140 years. 140 years. We are taking a relationship and we are solidifying our partnership by committing to working side by side in a synergistic way that will impact discovery, biomedical discovery, and take it straight to the clinic for the people of New South Wales and the world. I can't underestimate how exciting this is for the University of Sydney and the local health district. It is something that we have long dreamed of. It's something that few other places have achieved, and we're on the precipice of it. It's remarkable.
And it strikes me that this development may have been a long time coming, but it's arriving just at the right time. The impact of quantum, the impact of nanotechnology, the impact of AI means that all of these tools that are now available to our brilliant scientists and wonderful clinicians just gives them a repertoire that they can draw on, which should really help with discovery and translation.
Oh, absolutely. I think there are points in history where you can see there great leaps are possible because something has changed in the ecosystem, whether it is AI or the single patient digital health record or things like that. We are now committing to saying we are going to use these technologies for the good of these patients and also, I think, for the fulfilment of our scientists and clinicians. And I don't think that can be underestimated. The people that are delivering this work are committed to making the world a better place, and we are inviting them to do that.
And we're thrilled you're taking on that leadership role. That's Professor Victoria Cogger. She's the newly appointed inaugural Executive Director of the Sydney Biomedical Accelerator. And if you want to learn more about how diabetes researchers are leading us into the future of medicine, listen to our episode with Professor David James, who's working on precision medicine.
What I would like to see is if we could do a test on people right at the get-go, and that test would tell us you should be taking drug Y, so that you immediately prescribe drug Y, save all those problems, and you save the potential dangerous adverse effects from taking 4 medications instead of 1.
You can listen to that episode of The Solutionists right now, and make sure you're following the show so you don't miss an episode. The Solutionists is a podcast from the University of Sydney, produced by Dead Set Studios.